All right, here's just a quick overview of a couple of different types of ellipse applications, and we'll continue to work with these in class. All right, so a whispering gallery, many of you have probably been to a whispering gallery, whether you know it or not, but it's, you know, they're often elliptical in shape, or ellipsoidal, which is like a three-dimensional ellipse, so it would look like something like a sphere, but in ellipse form, right? So something like this. So they're ellipsoidal in nature. And two of the most famous ones are at the Capitol building in Washington, D.C., and the other one is in Grand Central Station. So you can literally stand at one focus of the ellipse and whisper, and someone standing at the other focus of the ellipse can hear you. So a lot of ellipse applications have to do with whispering galleries. So we have Jake standing at one focus of an elliptical whispering gallery is 6 feet from the nearest wall, and Carly is at the other focus 100 feet away. What's the length of this whispering gallery, and how high is this elliptical ceiling at the center? So in general for these, you can assume that that the ellipse is both the floor and the ceiling. So it's like an elliptical floor and then also an elliptical dome, and that, you know, the width and length of the floor is going to be the same as like the height of the dome. So it's like a symmetrical ellipsoid. All right, so if we draw our ellipse, right, and we have Jake is standing 6 feet from the nearest wall, so we'll call this focus Jake, and he's 6 feet. And then we have Carly, who's standing at the other focus, and she's 100 feet away from Jake. So the question is, what's the length of the whispering gallery? The first question. So the length, obviously, it's symmetric here. So we've got 100 feet here. We have 6 feet from Jake, between Jake and the wall. So we must have 6 feet between Carly and the wall as well. So the total length is just going to be 112 feet. All right, and then the other question is, how high is the ceiling at the center? That question is going to be answered also by saying, like, what's the width of the room, or not the width, but like half the width of the room. So like this minor axis, half of the minor axis, or the B value, is going to give us the height of the room as well, because it is all symmetric everywhere. So keeping in mind that we have this formula, c squared equals a squared minus b squared, that relates all those pieces of an ellipse, and we're looking for b squared, so that's what we're looking for here. We have c, right? If we know the total distance between the foci is 100, then c must be just half that distance, so 50 squared. A is not given directly to us, but we could figure it out, right? Because A is half of the length, so that's 56 A squared, and B squared is what we're looking for. And it looks like, so this would be 2,500 equals 3,136 minus B squared. So B squared is 636, which makes B approximately 25.2 feet. There we go. So the next example we have, another common example with ellipses, are elliptical orbits, right? And so this is an example of the Earth's orbit around the sun. So it's an ellipse that's almost a circle. Okay, so we're going to actually find out how close to a circle it is when we calculate the eccentricity in a little bit. The sun is at one focus, and the major axis is 299,190,000 kilometers in length, and the minor axis is 299,148,000 kilometers in length. So we want the minimum and maximum distances from the Earth to the sun. Okay, so we're going to assume that these distances are given to us, or when we find the distance, sorry, that we're kind of doing from center to center. So we're going to not necessarily assume that the diameter of the sun and the Earth are negligible. Although when we're talking about distances like this, you know, they might be, but we're going to just kind of assume we're going from center to center. So we're going to assume that that point, that focus, is right at the center of the sun, And then we're looking at, the center of the Earth being on the orbit. So the center of the ellipse is realistically like somewhere around here. Okay, and we're told that the major axis, and it's hard to tell, but the major axis with the ellipse with the orbits are going to be horizontal, right? So the major axis is 299,190,000, and then our minor axis here is this number. I'm not going to write it all down. Minimum and maximum distance from the Earth to the Sun. Okay, so hopefully it makes sense that the minimum distance the Earth is to the Sun is when it is, closer to the focus that the Sun, where the Sun is, and then the maximum distance is going to be over here, right? When it's on the total other side of the Sun. Okay, so the distance to the Sun over here when it's close can be calculated by finding out what is our A value and what is our C value, and then subtracting those two things. Okay, so the A value is easy. The A value is just half of this big number, right, which is 149,595,000. We'll calculate our B value just because we're going to need it to calculate C anyway. So B is half of this other big number here, so 149,574,000. Okay. So these are in kilometers. So we have an A and we have a B, right? But we've just said that if we take A and subtract C, that's going to give us this minimum distance here, right? So we need C. So we know that C squared is equal to A squared minus B squared. All right, so if we do a quick calculation, and I'm not going to write all these big numbers here because they are really, really huge, we'll find that C is approximately 2,506,501 kilometers, right? So the minimum distance is going to be A minus C. So if we take this number and subtract this number from it, we get approximately 147,088,498.7 kilometers. I'll put some commas so that we see. All right, so that's our minimum distance. So as the closest the Earth is going to get to the Sun is this distance. And then the maximum distance, hopefully we can see, right, if we take a look over here at our diagram, the maximum distance is over on this side of the orbit, and that's still A, but in this time, instead of subtracting C, it's just A plus C, right? So we can add A plus C, and we're going to get 152,101,501 kilometers. Okay, so those are some pretty huge numbers there. All right, the second question says, what's the eccentricity of the Earth's orbit? Remembering that eccentricity is simply the ratio of C to A, right? And if I take my C value of 6,501, right, 2,506,501, and I put that over my A value of 149,595,000. I mean, we could kind of tell those numbers are hugely different already. We should get something pretty darn close to zero, right? So this, when I do this calculation, I get 0.0168-ish. Okay, so this is a very small eccentricity. It is very close to zero, which is going to indicate to us that that orbit is indeed very close to being a circle. Okay, and this last example is not unlike some of the examples we did with parabolas. Okay, so we have a railroad tunnel. We could have had a railroad tunnel shaped like a parabola before. This one's shaped like a semi-ellipse. Okay, so we'll make it a little bit more elliptical than we would if it was a parabola. The height of the tunnel at the center is 44 feet, and the vertical clearance must be 22 feet at a point 9 feet from the center. So for just like with parabolas, we would often just place the vertex at 0, 0 to make our lives easier. With the ellipse problems like this, we're going to place our center at 0, 0 to make our lives easier, just like we would have if we were to write an equation for either of the other two that we just did as well. Okay, so we know that the vertical clearance must be 22 feet at a point 9 feet from the center. So if I go over 9, I didn't draw this very well to scale, but if I go over 9, then my vertical clearance is 22. So the point 922 must be on my ellipse. Likewise, the point -922 must also be on my ellipse, but we only need the 1 point. So we need an equation for the elliptical tunnel. Knowing that we're at 0, 0, we know our equation is going to look something like this. X squared over a squared plus y squared over b squared equals 1. So now we have a b value, right? We know b. And we know an x and we know a y. So we're looking for an a, right? This is the question mark. I suppose we could be looking for b, but I'm going to assume that this tunnel is wider than it is high because that's typically how tunnels look. So we can just plug in everything that we have at this point in time, right? So we can plug in our x value of 9. We don't know a. We have a y value of 22. And we know that our b value is 44, so 44 squared, all equals 1. If we do some simplifying here, we have 81 over a squared equals 484, oops, not equals, plus, 484 over 1936, that all equals 1. So we can do some kind of manipulation here. We can multiply all of this by 1,936a squared to get rid of those fractions, right? So 81 times 1936 is 156,816 a squared plus the 1936 here is going to, oh no, not the a squared, because that's that cancels. Sorry about that. All right, on the second term here, the 1936 is going to cancel, so we're going to get 484 a squared, and this is going to all equal 1936 a squared, right? If we subtract that 484 from both sides, it looks like we have 156,816 equals 1452 a squared. So a squared must be 108. That worked out nicely. And we're just being asked to write the equation for the elliptical tunnel, so I don't need to know what a is, right? So the equation for any point on this elliptical tunnel is going to be x squared over 108 plus y squared over 44 squared, which we learned was 1936, equals 1. And that's it. And now, I could extend this question and say, what is the clearance at a point, 11 feet from the center or something like that. So I could have you then use this equation for some, to find some more information. And that is it for different types of elliptical applications. And there's other variations of these, but they all kind of fall under, similar umbrellas. So we'll see some more in class.